separating it from chapter 7 here.
What is polyvinyl alcohol used for?
Polyvinyl alcohol. I'm not really sure. I wonder if the
Okay.
polymer, it must be a fairly water-soluble polymer. Polyvinyl alcohol. Polyvinyl chloride. Yeah, PVC, but polyvinyl alcohol, I'm not sure if that's a plastic. Yeah, it probably is. It probably is but it may be kind of a water-soluble plastic. Oh, I got this video. Let's see if let's see if I can start this video. Can I just touch that thing? No, can't do that. What can I do? Thought I'd be able to start this right off of this slide. What do I have to do? Copy that and paste that into a browser, I guess? Today has been a day of technical difficulties. I sent things to one printer and it was out of toner, and you can relate.
Yeah, last night was a night of technical difficulties.
Yeah, and I know, when time is of the essence, that seems to be when the technical difficulties come in. I hate to just go to YouTube because all kind of junk comes up.
All trending stuff.
All what, Grant?
All the trending stuff.
Yeah, all the trending stuff. Let's search ATP synthase video.
You want to edit it? Or what it could be?
What could it be?
Bias energy. The universal biological fuel is a molecule called ATP, or adenosine triphosphate. ATP stores chemical energy in the form of a high-energy phosphate bond.
This doesn't look like the one I wanted.
It consists of an adenosine ring with a chain of
ATP synthase. Well, maybe this is the right one.
bias energy. The universal biological
Because it'll still be ATP, but it's added triphosphate. But you have to switch to it.
No, I don't really think we'll have that. So we'll keep it.
to keep cells alive and is used from processes from muscle contraction to producing the thoughts your brain is having right now. The hydrolysis of ATP can be reversed by the addition of inorganic phosphate to ADP. However, this of course requires energy and is performed by a molecular power generator called ATP synthase. Here we see an atomic model of F1-FO ATP synthase sitting in a membrane. This molecular motor is found in the mitochondria of eukaryotic cells and is responsible for making most of the ATP.
Okay, this is about 4 minutes.
The powerhouses of the cells.
This is about 4 minutes, and then I'll tell you why we're using it to introduce Chapter 8. Okay? All right? So, and this isn't the one that is in the slide there. It's a different one.
60 kilograms of ATP every day in an adult person. A long chain of biochemical processes convert the energy stored in food into a proton gradient across the inner mitochondrial membrane. These protons drive a rotation of the turbine within ATP synthase, resulting in the synthesis of ATP. Like all generators, ATP synthase consists of two separate motors coupled together. Within the membrane, we have the FO motor, named after the binding of antibiotic oligomycin. And at the top, we have the F1 motor, from factor 1. The FO motor is a proton-powered motor. It is thought that protons flow through a channel open to just the intermembrane space, where they bind to a ring of protein subunits, rotate 360 degrees, and exit through another channel exposed only to the matrix. The net flow of protons, driven by the proton motor force, provides the energy for the generation of rotation. The torque generated in the FO motor is transferred to the F1 motor by a central stalk or shaft. The F1 motor is responsible for generating the ATP by addition of phosphate to ABP. The top of the central stalk acts similarly to a camshaft, so that as it rotates within the F1 motor, it causes conformational changes of the catalytic subunits. The catalytic unit is made of a dimer of subunits, and there are 3 of these arranged in a ring. Catalysis occurs at the interface between the dimers. If we concentrate on one dimer, we can observe 3 distinct states. First, ADP and phosphate bind to the catalytic site. The central shaft then rotates 120 degrees to rearrange the molecule. Next, the enzyme undergoes a further 120-degree rotation, and the ADP and phosphate are fused together to create ATP. The enzyme then rotates again to return to the starting position, where ADP is released, and ADP and phosphate can be bound for the next cycle of catalysis. One key aspect of this relationship is that catalytic subunits must remain stationary with respect to a rotating central shaft. This task is performed by a scaffold on the outside of the complex, referred to as the Griffel stall. Recent work has shown that what was once thought of as a rigid scaffold is actually dynamic and is able to accommodate changes necessary.
Let me just pause right there. A lot of things moving here in a very specific way. So what you have here is a protein motor. You basically do have a motor. You have a unit that is running in a certain direction. And this is the so we're talking about a lipid bilayer. Here's the mitochondria membrane. This is the membrane inside the mitochondria. The ATP synthase, so that's an enzyme. This is not one protein. This is a complex protein. So each one of these different areas here is a different protein molecule for a particular reason. The whole metabolism of glucose and glycolysis and then the Krebs cycle is funneling into an electron transfer chain, which is generating finally protons. And there's a proton gradient here. There's a high concentration of protons here, so we've got H plus particles here, subatomic particles here. And there's a very low concentration of protons over here. And so how does this flow back over to here? Through ATP synthase. So this is picking up a proton, and when this thing picks up that charge, it rotates. Picks up another proton, rotates. Picks up another proton, rotates. And dumps them out on the other side of the membrane. So, I mean, if you thought of a high dam, and gravity forcing water through a generator, we have the same sort of thing here. We have a dammed up amount of protons, and that gradient is being forced through this motor, through this thing here that is turning this whole thing and causing, so charged particles, protons, charged particles that are driving this whole thing, and a very elegant array of proteins that does not intuitively look random to me in any way. Looks very, very extremely well designed piece of equipment. And it's a piece of equipment, but it's made out of protein molecules with moving parts. They've done experiments here where they've actually tagged, they chemically attached a fluorescing little arm on the top of this. I'm not sure where they attached it. I don't know if they attached it here or up on the top of there. And they can actually watch under a microscope, they can actually watch that fluorescent thing twirling around, showing that this thing does move, has moving parts. All right, so all that to introduce electrochemistry. So that's what this slide was about. And like I said, I think that's a little bit, again, about a 4 minute long. Where am I? I need to get into this one. About a 4 minute long YouTube on ATP synthase. Extremely well studied protein complex and what it does and how it works, and so it's really phenomenal. And the body is using it to generate the ATP, thousands of them. I don't know how many, anybody know how many mitochondria there are in a typical cell? I mean, each cell has a bunch, and I don't know if it's 100, 1,000, how many mitochondria. I'm not a biologist, but lots of mitochondria, and embedded on those membranes are these ATP synthase, and that's what is synthesizing ATP. All right, so chapter 8. This is what you see on chapter 8. Charges, energy and work, standard potentials. And this part 1 goes down to about here, standard potentials. Not sure it gets that quite that far. And then there'll probably be at least 3 parts to this as we go through this chapter. When we started chapter 7, I paused. Remember, I wrote on the board, here's a whole bunch of symbols. You're going to have mole fraction in the solution, mole fractions in the vapor phase. Well, there's going to be a whole bunch of new symbols in chapter 8. And we're going to even use the letter F 2 different ways. The way you're familiar with it is force, and then a kind of a calligraphy or handwritten F, Faraday's constant. 2 epsilons, and they're very different from each other. Epsilon naught is this permittivity of free space. It actually is a constant, is a number. Epsilon sub r, that's an r there. That's the dielectric constant. Electric field, electric potential.
Do you have the constant on here?
Dielectric constant? The dielectric constant varies with the material.
Okay.
So different materials have different dielectric constants. So a lot of these here are these aren't all constants. These are symbols. This is a constant. This is a constant. The charge on an electron or a proton. Equal charge, opposite sign. And then if you take the charge on an electron or proton times the Avogadro's number, you come up with this Faraday's constant. And just a caution, if you multiply this times this, you don't get that. It's a little bit different. And I'm sure when they write out that constant, they're carrying that out to many more decimal places. So go off of this as Faraday's constant. You open up the front of your textbook, this is what you'll see for Faraday's constant. That number. But what is it? It's a mole of electrons. It's a mole of electrons times the charge on each individual electron or proton. So it's 96,485 coulombs per mole. So before we start looking at a whole bunch of equations, and I'm not even sure that's all the symbols. Those are the major symbols in chapter 8. And this next slide is some of the key equations. So don't think that's a derivation down through here. This is just pasting up here a number of key equations. We'll look at a bunch of these individually. There's about 4 pages of derivation that gets you down to here. 4 pages. It kind of starts at one point, and we won't get to here today, but we can just start dipping our toes into this a little bit. Okay, and it just starting out, so in electrochemistry we're going to be seeing the movement of charged particles. So, and what is the force between them? So if you just had 2 charged spheres, didn't even think of electrons and protons, just two things that had charge on them, the force would be inversely proportional to the square of the distance between them. The further apart they get, the force of attraction or repulsion between those charged particles is going to decay quickly with distance apart. They get closer together, that force is going to magnify it with the square of that distance. And then the other thing is it's directly proportional to the magnitude of the charge on the spheres. All right, so inversely proportional to the distance between them, directly proportional to the magnitude of the charge. And you move from here, you can get it into an equality by introducing this permittivity. Epsilon naught is the permittivity of free space, a number. And it gets you into a force that's in SI units. And maybe we don't need to go any further than that, but just start getting familiar with the first 8 or 10 pages of chapter 8 and some of the symbols that are being used there, and we'll derive and do some examples on Wednesday. All right? And by Wednesday you should have a little better feel for what questions you have on chapter 7 homework.
Are we going to have chapter 8 homework soon?
Hopefully.
Yes.
I haven't started pulling it together yet, but I'll try to get it to you. All right.
Oh, what did you do?
What happened?
Do you know, is anything happening in career comp tonight?
No, I have no idea.
I kinda
I didn't
wanna
put anything on Moodle, so.
I kind of want to skip it.
Same. I want to skip it too, and then I just remember him always complaining about it every day.
Because she said we have that, quote, big assignment due mid